Hey everybody, hope you're doing well. Today I have a video for you on optics diagrams, and my goal today is to go over all of the core diagrams that you'll be expected to know about in your physics unit for grade 10 science. So let's jump right into it. Usually you'll start with straight mirrors, as those are the most simple. We have an object in front of a mirror, and the way I know how to draw the image that's going to be formed is I just need to record the distance from my object to the mirror. So let's pick a point on our object. We have an arrow here. I'm going to start at the base. And let's imagine that the base is about 5 centimeters away from the mirror. What that tells me is that there's going to be an image formed behind the mirror 5 centimeters away as well. And that's where the point, or the base of our image arrow will form. Let's pick another point. I'll pick the other end of the arrow, so the tip here. Let's say that this is 7 centimeters away. So it will be 7 centimeters behind the mirror. And that allows me to draw my image. Now this will be a virtual image because light is not passing through the mirror and converging at a point. What's actually happening is we have a light source hitting the object, bouncing back at the same angle, and then virtually we can extend our reflected light backwards, and you'll see that that's where it hits the end point of our image. So if you need to show proof as to how you got this image, you can use your angle of incidence. Let's say that was like 15 degrees. And your angle of reflection will be the same. So it's coming in at 15 degrees, bouncing back at 15 degrees, and then we extend the reflected ray backwards virtually. And usually what we want to do is we want to pick 2 different rays of light to prove this at different angles, because that'll tell us where virtually the light would converge. So we could also do that on the second point that we used, but just to save time, let's move on to our next example. Okay, now we've got curved mirrors. We're going to start with concave mirrors. Now, concave just means that the mirror is kind of caving in towards you, assuming you're starting on the left side. And we have F and C here. All these mean is focal length and center of curvature. So if I were to kind of extend this mirror and create like a full circle, that's a horrible circle, but you know what I mean. This would be the center of that circle's curvature. So that's all that means. And then F is our focal length, which is going to be half the distance from the center of curvature to the mirror. And that's just where light tends to converge. So I'll just make some small dots here to mark C and F a little bit better. Okay, so for a concave mirror, we have a few different rays of light that we can use to solve for the image. First one is going to be parallel to the principal axis, and the black line down here is just the principal axis. And then it's going to bounce back through F. Our second ray of light will go directly through F, hit the mirror, and then bounce back parallel. And what you'll find is our 2 rays of light are going to converge at some point, and that tells us where the top of our image is going to be. So that's where the image of our arrow will be formed. There is one more ray you could use to solve here. We could shoot a ray of light that goes directly towards the middle of our mirror. And what happens here is exactly what happens in our straight mirror example. The angle of reflection is going to equal the angle of incidence, and it should converge at the same point. So if you need a third ray, sometimes teachers will ask for 3 rays to prove an image for a concave mirror. We can use that third ray. Okay, what if we wanted to describe our image? Usually a test will ask you 4 specific characteristics of an image. First, we have L, which is location, and I can see that our image is going to be in between C and F, so that will be my answer. O, sometimes this is also an A, so it could be orientation or attitude, and really all it's asking is your image pointed upwards or downwards? We would say upright or inverted. In this case, it's inverted. S is size. It looks to be a little bit bigger than our original object. So let's say larger. And T is for type. So it's either going to be real or virtual. Remember in our straight mirror example, the light reflected back on this side of the mirror, and we were only able to form an image virtually by extending those rays beyond the mirror. So this would be a virtual image. But in our concave example, we actually have real rays of light converging at a point. So this will be a real image. Just jumping in quick to make a correction. I mistakenly said that the image in this scenario would be larger, but it's actually going to be smaller. So I'm going to redraw the diagram with the same ray rules. So we're going parallel, then back through F, and then we're going through F and back parallel. So this is a little bit clearer, and you can kind of see that our image is actually slightly smaller than our object. So sorry for that, but let's get back to the video. Okay, moving on to convex mirrors. And we have a couple of different rules, so it's important to know the difference. Let me mark my points here for F and C. And if you're wondering about the difference between the F and C here and the F and C here, is that technically a convex mirror is a concave mirror that's been flipped, right? Because now we're on this side. So the center of curvature naturally would go there with the curvature of the mirror. So just to represent the same distance of F and C, we mark F prime and C prime on our left side. First rule or ray, we are again going to go parallel to the principal axis, but instead of focusing on our F on this side, it's actually going to bounce away as if it came from our focal length right here. And what we can do is we can extend that ray virtually beyond the mirror. Okay, that's one. Second one is going to travel as if it wants to get to F on the other side, right? So it's trying to get here, but it gets stopped by the mirror and bounces back parallel. And again, we can extend our reflected ray backwards. And voila, we have a point where our 2 virtual lines have converged, and that's where our image is formed. But we do have a third ray if we need some more proof. When a ray tries to get to C on the other side, it's actually going to bounce back following the same path it traveled to get to the mirror. So that'll just be a straight line as if we're going to C. And then we can extend that one virtually as well. And it should hit the same point of convergence. Okay, let's see if we can describe our image. The descriptions may vary depending on what your teacher is looking for, but I'll just give you the characteristics or descriptions that I'm used to using. So in this example, I could say the location of our image is behind the mirror, between the mirror and F. O is orientation or attitude. This time it looks upright. Size, it is noticeably smaller than our object. And type would be virtual, because we had to extend our reflected rays virtually beyond the mirror or behind the mirror to get an image. All right, so that is the basics for concave and convex mirrors, but we do have some special situations that I want to go through, specifically for concave mirrors. Our first special situation is going to be when our object is directly on our focal length. And what's going to happen here, no matter what, no image will form. So if you're dealing with a concave mirror and you see your object at F, you know right off the bat, okay, no image is going to be formed. However, we may want to show some proof for that, so let's do that. Let's try and follow the first ray rule for a concave mirror. We're going to go parallel, and then the light is going to try and go back through F. Okay, that's fine. But if I try to do my second ray, which needs to go through F first, I can't really do that, right? Because we're on F. Okay, well, what if we did something with C? Because, like I mentioned in the convex example, light that's traveling away or towards C will just bounce back in the same direction. So let's imagine I'm traveling away from C, hit the mirror, and then bounce back through C. Well, you'll notice these two lines are going to go on forever and never meet at a point because they're parallel to each other. And even if we were to extend these lines virtually, we still don't get converging light. That's why no image will form. Moving on to our second special situation, the object is now between F and the mirror. So let's try the usual rules. We're going to go parallel. We're going to try and go back to F, but we kind of get stopped by our object, right? It's in the way. So we'll leave that for now. And then I can't go through F again because we're beyond F. What if I used the third ray, right? Because we could use the third ray to show an angle of incidence here and then an angle of reflection here. So let's say that's like 30 degrees. And then what I can do now is extend my two reflected rays virtually. So this would be my reflected parallel ray. We're going up like this. And then my angle of reflection ray will be more like this. And here we do have a virtual image formed. So instead of getting normally a real image sort of around on this side, right? We're going to be getting either no image forming or an enlarged virtual image on the opposite side. Okay, that about sums it up for mirrors. Let's move on to lenses. So lenses act a little differently because light will always travel through a lens. So we're not really dealing with angles of reflection anymore. And I'll explain that a little bit better with our first example of a converging lens. That's when the ends of the mirror sort of converge together, right? First ray is again going to be parallel, and then once it hits the middle of our lens, it'll bend towards F. And then our second ray is pretty simple. We're just going to go right through the middle of our lens, and it will continue to follow the same path at the same angle. And that should give us a point here where the light is converging, and I get a real inverted image. And it's real because these are the real rays of light passing through the lens and converging at a point. All right, not too bad. Let's move on to diverging lenses. And diverging lenses are just referring to the fact that the mirror is kind of pushing outward and diverging away at the ends. That's how I remember the difference between converging and diverging. If you guessed by now, our first rule is going to be going parallel to the principal axis, but this time the light is going to bend away from F on this side. And so what we can do is we can extend our bent light backwards. And that will be a virtual line. Our second ray is going to travel trying to get to F on the other side. But as it hits the middle of the lens, it bends out to be parallel to the principal axis. And then here we can extend our ray backwards. And we should get a virtual image converging at a point. But we're not done yet. Just like with concave mirrors, converging lenses also have some special situations. And they are very similar to the concave special situations. So first one, we've got our object at F. Once again, no image is formed. How do we know that? Well, let's try following our usual rules. We're going to go parallel through F, and then we're going to go straight through our middle. These lines are parallel, and so they will never give us an image. And lastly, we have an example where the object is in between F and the converging lens. And I just noticed that this should not say mirror, this should say lens. There we go. So let's use our usual rays for converging lens. We're going to go parallel to the lens and go through F on the other side. Okay, and now let's go through the middle. So as you can see here, at this point, our rays are not parallel. They're slightly diverging away from each other. So that means if I were to extend my rays virtually backwards, there should be a point where they would meet up. So in this case, we're going to get a very enlarged image way back here. I'm even going to have to extend my principal axis just to have it show up there. So this would be a very enlarged virtual image. Okay, I think that's about it for today. That covers quite a lot. But again, the optics unit does cover quite a lot, and I thought this video would be useful to just summarize all the different rules that you're expected to know. So here's a quick little overview of everything we went over. So if you would like to go back to the end of this video every now and then, just to do a quick review of all of the lens and mirror diagrams, feel free to do so. Thank you for watching, and happy studying.